Hi, my name is Sasha Angelina Cardona Lopez, and today I want to talk about the structural behavior of slender reinforced concrete columns with GFRP under various centrity loading conditions. This topic is based on a research article written by Russell Haim and Hassan F. Hassan in 2022. Published. GFP is a composite material made of glass fibers embedded in a polymer matrix. It has several remarkable characteristics. It is much lighter than steel. Its density is only about one fourth or one fifth of steel's. It has a high tensile strength, sometimes even comparable or higher than steel. It is corrosion resistant, making it ideal for aggressive or marine environments. It is non-conductive and non-magnetic, which makes it suitable for electromagnetic sensitive areas. However, one limitation is lower modulus of elasticity, meaning the force more under the same load compared to steel. This article specifically focuses on slender reinforced concrete columns that is tall and relatively thin elements where the formation and buckling effects become more significant. The columns were fully reinforced with GFRP and were tested under two types of loading: concentric loads, where the force bases throughout the centroid of the column, and eccentric loads, where the force is applied off center, creating a bending moment in addition to compression. The main objective of the study was to evaluate the load carrying capacity, the failure modes, and the ductility of these columns. This research is highly relevant because the construction industry is increasingly demanding materials with better durability and performance. In aggressive environments such as coastal zone, chemical plants, or wastewater facilities, steel reinforcements deteriorate very quickly. Using GFRP can significantly extend the service life of the structure while reducing maintenance costs. Now let's talk about the methodology and testing program. The researchers prepared 16 reinforced concrete columns, each with a square cross sections of 140 by 100 by millimeters and a height of 1.2 meters. These columns were divided into several groups to analyze for main variables: type of reformers, longitudinal reformers radio, and tight spacing and centrity of the lot. They tested three levels. During the test, they measured the formation, displacement, and applied forces using several instruments. LDBTS for displacements, strain gauges to record bar strains, load cells to measure the applied load, and a data logger to continuously record all measurements. Now let's discuss the main results obtained from this experiment program. First, as expected, columns under concentric load higher load capacity than those under concentric load. This happened because eccentric loads produce bending moments that reduce the effective compressive strength of the section. Regarding the type of reinforcement, the hybrid columns achieved the highest load capacity, followed by steel-only columns than the GFP-only columns, which still perform as close to steel but with a slightly lower strength. When comparing reinforcements radio increasing, significantly increased the ultimate load of the columns. The tight spacing also had a noticeable influence. Under concentric loading, tighter spacing, 16 millimeters, improved confinement and strength, but under eccentric loading, wider spacing produced better load performance because it allowed more flexibility and prevented premature cracking. Finally, when analyzing the utility, the ability of the column to deform before failure, it was found that GFRP reinforced columns were more deformable than the steel ones, which is a positive aspect for seismic design. From all of these results, several important conclusions can be drawn. GFP is a viable alternative to steel reinforcement, especially in aggressive environments where corrosion is a major concern. The behavior of slender columns strongly depends on both the type of reinforcements and the loading conditions. Hybrid columns combining steel and GFRP showed the best overall performance, while GFRP only columns still exhibited competitive strength and better utility. The reinforcements radio and tight spacing are critical design variables that control the load capacity and failure mode. Finally, GFRP reinforcement provides enhanced formability and energy absorption, which is less advantageous in seismic or dynamic scenarios. To conclude, the research clearly demonstrates that replacing steel with FRP is not only possible but also beneficial in many structural applications. And GFRP can ensure longer service life, lower maintenance, and adequate mechanical performance even in slender columns subject to complex load condition. Thank you very much for this one. We will move we will move on to the following article. The paper titled Seismic Performance of HRC Beam Column External Joint with Node Stirrup and Reduced Encouraged Length in Core Region. It was published in Archives of Civil and Mechanical Engineering in 2024 by Wei Hao Mao and colleagues. Reinforced concrete or RC frames often fail at the beam column joint during earthquakes. This joint is very important because it transfers the forces between beams and columns and controls the ductility of the whole frame. Traditional joints need many stirrups and long encouraged lengths, which cause steel congestions and make construction especially for structures. The researchers want to develop a new type of joint using a special material called EG, which means hybrid fiber reinforced strength hardening cementitious composite. The main idea was to make a joint without stirrups and with a shorter encouraged length while keeping excellent seismic behavior. EG or ERG is a mixture of steel fibers and polyethylene fibers. It can stretch and crack in many thin lines instead of breaking suddenly. This behavior is called strength hardening. It makes the material very ductile, meaning it can deform a lot before failure, and it also holds the steel bars very highly and provide the bond. The team tested 5 stereo joints under cyclic lateral loading. One was a normal RC joint and 4 were isolated RCO joints. The HC used in the study had compressive strength of about 55 megapascals, a tensile strength of 6.8, and tensile strength capacity of about 4%. It contained 1% steel fibers and 1% polyethylene fibers, giving it high toughness and excellent bonding. Each specimen was rotating 90 degrees, so the beam was vertical. The column carried a constant axial load equal to 10% of its capacity. Add hydraulic jack applied cyclic forces to the beam tip. Displacements and rebar slip were measured using LVDT sensors. Failure models. Too many types of failure were sourced. Fractured failure at the beam end encouraged. When the specimens were loaded back and forth, the load displacement score shot plume and stable history lobes for all head joints except F4. This means they dissipate energy well and maintain strength. And Heck 4 showed pitching caused by bar slip because the anchorage was too short. The specimens could dissipate large amount of energy during cyclic loading. Strength degradation was small for all them. Heck 5, which had a higher steel radio for 3%. Measurements of bar slip showed that anchorage length of 9D was enough for wall-bound performance. Only the 6D specimen 5 by pull out. This means that using Heck allows engineers to reduce the required anchorage length without losing safety. In summary, Heck can replace stirrups completely in the joint core. The anchorage length can be reduced to 9D safely. The joints show similar seismic performance to normal RC connections. To conclude, Heck provides excellent confinement and bond strength. It enables the elimination of stirrups and a shorter anchorage length, simplifying construction. The study recommends developing a design method for Heck joints for real engineering applications. Thank you for listening.